Okay, so good morning. And in previous class, we were discussing about the thermal stresses. Okay, so after that, composite bar problems. Okay, we have seen some problems, and then I was talking about this temperature stresses or the thermal stresses that we have in our members. Okay, so all right. So coming to this temperature stresses. So as we have increase in the temperature, we'll find that the materials expand, and with the reduction in the temperature, the materials contract. Okay, so this expansion and contraction can be estimated or calculated by knowing the change in the temperature, the coefficient of thermal expansion. Okay, if I am interested in only one dimensional change, okay, that is a change in the length. Okay, so I'll be dealing with linear expansion, coefficient of linear expansion. Okay, or else if you are interested in volumetric expansion, then this coefficient will be for entire volume, like that. Okay, so but in any case, this is required, coefficient of thermal expansion or coefficient of linear expansion. Okay, so with this, we can estimate what will be the increase in the length here. Okay, like for example, in this case, this is a bar AB of length L, and the temperature has increased from T1 to T2. Initial temperature was T1, and the final temperature is T2 here. Okay, so what happens due to that is this bar length will get increased. Since temperature is increasing from T1 to T2, there will be increase in the length of the bar, right? So which is given by this alpha into T into L. Okay, so alpha, that is the coefficient of linear expansion. It will be expressed in terms of per degree rise in temperature. Okay, T, whatever the change in the temperature is there, that is final temperature minus the initial temperature into the length of the member. So this is the change in length. Now with this, if you want to find what is the strain, okay, then I can easily express this strain. What is the change in length divided by original length over here? So that strain can be obtained. Okay. Now suppose in case if you have free expansion, then there's no question of any stresses arising here. So this member will freely expand without any the stresses which are there. They will not get developed. There will not be any temperature stresses developing in this uh, bar, if at all, if it is allowed to expand freely like this. Okay, in case this expansion is restrained, say I don't allow this bar to expand by any amount, then they will come across the temperature stresses in that case. Okay, so how much will be the temperature stresses? So that can be estimated if we find what is the stress developed due to this deformation. Now what I'll do is I'll bring back this deformation. Okay, I'll make this expansion due to change in temperature zero by applying a force like this. Okay, so I'll apply a force, and then this I'll bring it back to zero. So what I'm actually doing is I'm contracting this bar. I'm inducing a compression in the bar over here. Okay, so how much is this change in length? It is delta L again. What is the original length? For me, I started once the expansion has occurred in the bar. Okay, so original length was L plus delta L. Okay, so free expansion was there initially. So once it was allowed to expand freely, the length becomes L plus delta L here. Okay, now what I'm doing is I'm making this delta L zero now here. Okay, so initial length is L plus delta L. What is the deformation that I am causing in the bar is delta L. Okay, I'm making this delta L zero. I'm compressing this bar by delta L. Okay, so change in length is delta L, whereas initial length is L plus delta L. So this ratio is my strain now. Okay, now normally what happens is this change in length will be small when you compare it with this length of the bar. Okay, when I compare the length of the bar and whatever the expansion that has occurred, so this delta L will be very small. Okay, say for example, if you observe the railway tracks, you find small gaps somewhere in between. Okay, so if you compare that gap with the length of that rail track, it will be very small. It will be hardly some 5 mm, whereas a rail track will be running in some meters, 10 meters, 15 meters, like that. Okay, so this delta L, I can neglect this in this term, in this strain, in the this sum, that L plus delta L. Okay, so I can neglect this delta L. It is very small compared to L. So I can simply write it as delta L by L only. My strain will be delta L by L, change in length by original length, which we are taken it as L itself, simply L. Okay, so I know the strain. Now what I want to know is what is the stress in this bar. Okay, so stress I can obtain by considering the Hooke's law here. Okay, so if I use this Hooke's law, which is ratio of stress to strain, I want to know what is the stress in this bar. So it will be simply strain multiplied by the modulus of elasticity E. So this is what is done, strain, okay, delta L by L into E, or what it comes out, my delta L is nothing but alpha T into L. Free expansion delta L was alpha T into L, right? So alpha T into L divided by L into E. So this stress is alpha T into E. This is the stress due to change in temperature. This is what the stress is coming in that bar. Okay, so this is our expression for the stress due to change in temperature, alpha T into E. Is that clear? We first observed the free expansion of the bar, okay, without any uh, this one without preventing the deformation, and then the same expansion which was occurring in the bar was made zero. Okay, so with that, what happens is this is my actual bar now, L plus delta L of length L plus delta L, and I am compressing this by delta L. So strain will be change in length delta L divided by original length L plus delta L here. Okay. What I did was I neglected this term delta L since it is very small compared to this L. So this delta L has been neglected in this denominator. So finally, it just tells me strain is equal to delta L by L. If I want to find the stress sigma, it will be epsilon times the E. Okay, strain multiplied by modulus of elasticity. So here I have my strain delta L by L into the modulus of elasticity. Or else, what was this delta L equal to? This was alpha T into L. This is what the expansion of the bar will be under the change in temperature. So if I substitute for these terms, what I get is stress will be alpha T into E. So simply alpha T into E. Okay. Or if you want the force in the bar, multiply this stress with the area of the bar, cross-sectional area of the bar. That is sigma into E. It will tell you what is the force that is developed in this bar due to the change in temperature. When this happens, when this stress develops is when you prevent free expansion, when you restrain or prevent this free expansion. Only at that time, this stress will get developed. Or else if you allow it to expand freely, no stresses will be developed in those bars. Okay. So that is the purpose. You'll find in some places gaps are provided for free thermal expansion to prevent any stresses being developed in the material. If you observe the concrete roads at certain length, they will provide the gaps over there. Okay, so those gaps are meant for the concrete to expand freely, so that no stresses will get developed in that material. That is the purpose. So we try to avoid such stresses, normally thermal stresses, by providing such expansion joints or expansion gaps in the case of railway tracks and so on. Okay, but if you want to estimate the stress developed due to the thermal expansion, this is our expression. Okay, so this will happen only when that free expansion is restrained. Okay, you have any doubt in that? The temperature stresses, how do we find the temperature stresses? Sigma given by alpha T into E. This expression, this is the expression for temperature stress. Is the derivation or the concept of temperature stresses clear for all of you? 18 CV 10. Are you there? 18 CV 010.
Yes, sir.
Is that clear? Any doubt in that part?
No, sir.
Who is a 19CV008? 19CV008.
Yes, sir.
Uh, how do you find the temperature stresses expression? What we obtained finally? Like, did we get any expression for temperature stresses? No, you're not there. 19 CV, 18 CV 041, 2KL 18 CV 41. 19 CV 008. No, don't know. Still in doubt, confusion. 19 CV 014. These will be there for your first internal, which will be on Monday, I think. Others, if you don't have any difficulty in understanding this, we can proceed further over here, or else you can ask me if you have any difficulties. Okay. So what we just discussed was in case of one single material. Okay. When you have one single material. Now, in case if I have two materials joined together. Okay, see, in this case what we are considering is an example of steel and brass. There are two members, one made of steel, other made of brass. They have been rigidly attached with each other. Okay, this joint will not allow any free movement of these two bars. Okay, independently they cannot uh, deform. Okay, so they have been connected very much rigidly. They have been glued properly at this joint. That is what we can say. Okay, now let us say this holds good for any two materials of different properties. For simplicity, in this derivation, we'll be considering this steel and brass. Okay, so this is what we have here. Now here, the properties for this steel, let us say A1 is the cross-sectional area of this steel bar. E1 is the Young's modulus of that steel. Alpha 1 will be our coefficient of thermal expansion for the steel. Okay, so these are the properties for steel. Okay, with the suffix 1 1, A1, E1, alpha 1, they are the properties of steel bar. Now, similarly, for the brass, the properties are E2, the cross-sectional area. E2 will be our modulus of elasticity for brass, and alpha 2 coefficient of thermal expansion for the brass, this bar. Okay, so here if you see, brass has a higher coefficient of thermal expansion compared to steel. So alpha 2 will be greater than alpha 1. Okay, so this is how it is in considering this example here. Alpha 2 is greater than alpha 1. Okay, now what happens if they are free? If the two bars are separated, so this would be the expansion in the two bars. Delta 1 will be the free expansion in steel bar. Delta 2 will be the free expansion in the brass bar. Okay, this is how it happens. Okay, since alpha 2 is greater than alpha 1, you'll find that deformation or thermal expansion in brass bar is more than that of steel. Okay, now when we have both of them connected, okay, like this, what I said was this joint is perfectly rigid. Okay, so it will not allow any free expansion, independent movement of these two bars. Okay, in this case, what is going to happen? So the deformation will be somewhere in between delta 1 and delta 2. Okay, neither the brass bar is allowed to freely expand up to delta 2, nor the steel bar is expanding only up to delta 1. It will be pulled beyond delta 1. This will be held below this delta 2 value. Okay, so that is how these bars will behave when they are joined together, okay, as a composite bar. Okay, so we will find that the expansion of that composite bar will be somewhere between delta 1 and delta 2, more than delta 1, less than delta 2. So what is that expansion? What stresses will be developed in both of these materials if they are connected together, if they are used as composite bars? Okay, so what will be that? So here what happens is, we saw that expansion of brass is more than expansion of steel. Okay, Now what happens due to this? There will be compressive stresses which are developed in the brass bar because it is being pulled back by the steel bar. Steel bar is not allowing the free expansion of this brass. Brass tries to expand up to delta 2, but steel cannot move that much freely. So it is trying to restrain this deformation. It is trying to hold back this expansion of delta 2. So that is causing a compressive stresses in this brass bar. Okay. Now what is trying this brass bar trying to do on steel bar? It is trying to pull this steel bar beyond delta 1. Okay. So it is trying to stretch it beyond delta 1. So this will cause a tensile stresses in this steel bar. Okay. So that will result in a deformation delta in this composite bar. This is a delta composite bar deformation. So what you find is some stresses are developed in both the bars of different nature. Brass, it is having compressive stresses. Steel, it is having tensile stresses. Okay, just observe this carefully. Steel bar, what is our brass bar doing? It is trying to pull the steel bar beyond delta 1. Okay, it is trying to pull it or extend it beyond its free thermal expansion, whereas steel bar is holding back the brass bar. Okay, it is not allowing the brass bar to expand up to delta 2. Okay, so because of that, the stresses are induced in these materials. Okay, so tensile stresses are induced in steel bar and compressive stresses are induced in brass bar. Okay, keep that in mind. So two types of stresses in two bars. Now I want to estimate what is the total deformation delta in this composite bar, and also what are the stresses developed in these two bars. Okay, so say sigma 1 is the stress in steel bar and sigma 2 is the stress in brass bar. Okay, so what is the force in each of them? We'll obtain some expression for this sigma 1 and sigma 2 later, but what is the force in the both the bars? So what I have to do is sigma 1 into A1, sigma 1 stress in steel bar into the area of steel bar will be the force in the steel bar. Okay. Similarly, sigma 2 stress in brass bar multiplied by the cross-sectional area of brass bar is the force in brass bar. Okay. Or in this second bar. So for equilibrium, these two forces should be equal because we are not applying any external force on this composite bar. There is no external force acting on this composite bar. Whatever stresses or the forces are developed in these two bars, they are purely due to change in temperature. They are thermal stresses. Okay. So since no external force is acting, this sigma 1 E1 has to be equal to sigma 2 E2 for equilibrium. Okay. Or sigma 1 A1 minus sigma 2 A2 should be 0. Okay, so that is the equilibrium condition what we have. This is one condition here at this point. Okay, we'll keep this condition, we'll use it somewhere else later. Right now, coming to the expansion now. So what happens now when you connect both the bars together? When you connect both of them together, what we observed was the total deformation was delta. Okay, so what it should indicate, the expansion of steel bar, the total expansion of steel bar. This is, I am talking in the composite bar, not the separate bars individually. Okay, I am talking about what this over here. I'm talking about this expansion. The total expansion is what in this composite bar? Delta. So what I can say is expansion brass bar should be delta, and expansion of steel bar should also be equal to delta. That is, expansion of steel and expansion of brass should be same. Okay, in this composite, if they are free, they will expand by different amount, but now we have connected them together rigidly, so expansion or deformation in both of them should be same delta. Okay, so let us try to evaluate that. So what I have here is expansion in the composite bar, expansion of steel should be equal to expansion of brass, which is equal to delta here, right? Now what is the expansion of steel? Okay, in that composite bar, it will be free expansion plus elongation due to the tensile stresses. So what I said is steel, tensile stresses will be developed because brass bar is trying to pull it beyond delta 1. Okay, so free expansion of the steel bar delta 1 plus some additional expansion because brass bar is pulling it. That is tensile stresses, whatever the tensile stresses are developed in that steel bar multiplied by the this that strain developed in the steel bar multiplied by the original length. Okay, L was the length of that steel bar. So this is how we can get this expansion, strain into original length. Okay, so alpha 1 T into L. Okay, this is our free expansion. Okay, delta L we had expressed in this previous derivation. What was that equal to? So this is what this is alpha T into L, the delta L formula what we had seen just in the previous slide. Okay, alpha T into L. This is the free expansion given for any material, alpha T into L. Plus what? I want to know what is the elongation of steel bar due to the tensile stresses which are developed in it. Okay, so how I can get? First is I have to express the strain, which is what? Strain, stress by strain is constant. So stress upon E here. Okay, this is my strain. Also, what you have, strain is nothing but change in length. This is the change in length in our case now, delta divided by the original length L, right? What I am trying to estimate is what is the elongation delta here. I want to know what is this delta. So I can write delta is equal to epsilon into L. What is epsilon? Sigma by E. Or in case of it is a steel bar, we have taken this as sigma 1 and E1. So sigma 1 by E1 into the length of the steel bar. This is free expansion. Plus what is this? Here, this is the expansion due to the tensile stresses what we have taken in the steel bar. Okay, please make this point clear, very, very clear here. What I'm trying is what is the expansion in the steel bar. I'm trying to calculate that. One will be the free expansion, which is given by this free expansion. It is expressed as alpha into change in temperature, okay, into the change in temperature T into the length, coefficient of thermal expansion into change in temperature into the length of the member, alpha T into L. This is the free expansion term. Plus elongation due to tensile stresses. So what is really that? Whatever is the strain, tensile strain, multiplied by the length. Okay, that will give me. Or this will be nothing but sigma 1 stress by E1, tensile stress in the steel bar divided by its modulus of elasticity is this epsilon strain multiplied by L. Okay, L is the length of that steel bar, right? So that has been substituted here. I have substituted this particular term. This is the elongation due to tensile stresses. This term is giving me elongation due to tensile stresses over here. Okay, is that fine? What we are arriving at? What is the expansion in the steel bar, or what is the elongation of the steel bar that I am trying to estimate? This is one. Now, similarly, if I take brass bar, okay, so in brass bar, what will happen is brass bar, what I have to do is brass bar is allowed to expand up to delta 2. Okay, freely it can expand to a delta 2. Okay, but there are some compressive stresses that are developed in the brass bar because steel is holding it back. So what I should do is it is being compressed. So that will be epsilon 2 into L2. Whatever is the strain in the brass bar multiplied by its length will give me what is the change in length, what is the reduction in length. It is not allowed to expand up to delta 2. Okay, it is being pulled back by the steel bar. So what is happening in that process? There are compressive stresses that are developed in the brass bar. Okay, so what are that compressive stresses? Sigma 2. From that I can obtain what is the strain, compressive strain, sigma 2 by E2, that strain into the length, original length, L. L1 and L2 are same. So this is, okay, I don't have to take this as, okay, yeah, as L2. It is simply L over here. So epsilon 2 into L, or it will be, the strain can be put in the form of stress by Young's modulus, sigma 2 by E2 into L. So the final deformation in the brass bar, okay, this is also what? This is also delta only, which is equal to delta 2 minus sigma 2 by E2 into L. Okay, so here that has been put over here. this delta, okay, free expansion will be alpha 2 into T into L, okay, coefficient of thermal expansion into change in temperature into length. So this is delta 2, okay, it can expand up to this amount freely. But due to compressive stresses which are developed in the bar, it is undergoing a reduction in the length, which will be this alpha 2 T into L minus sigma 2 by E2 into L, this term. Okay, so now both of these A and B are nothing but delta. They should be same. So this has been equated here. Okay, so elongation of steel bar should be equal to elongation of copper bar. Okay, so that is what has been done. So what is the total elongation? It is delta in both the cases. Elongation of steel bar is also delta. Elongation of copper bar is also delta over here. Okay, so if I equate both of them, okay, what I get is this one expression over here, right? So now what I have is these expressions wherein I have sigma 1 and sigma 2. This is one expression containing sigma 1 and sigma 2. There was one more expression earlier. What was that? For equilibrium, this sigma 1 A1 should be equal to sigma 2 A2. Okay, expression number 1 is there, and here expression number 3, one more expression. So in both of them, sigma 1 and sigma 2 are unknowns. Two expressions and two unknowns. So we can obtain what are the stresses developed in these two bars. What is sigma 1 and sigma 2 can be calculated if we solve these two equations. This is one equation, sigma 1 into A1 is equal to sigma 2 A2. And this is one more expression what we have from arriving due to deformation in the bars. Okay, so using these two conditions, okay, we'll be able to get what is sigma 1 stress in steel bar and stress in brass bar. Okay, they may be other than steel and brass also. It may be aluminum and copper also, like that. But sigma 2 is greater than sigma 1 in this expression. That you need to remember. With that assumption, we have developed this expression. What happens here is, alpha 2 is more than alpha 1. Coefficient of thermal expansion, alpha 2 is more than alpha 1 in this expression. That is the condition what you have. If alpha 1 is more than alpha 2, this sign will change. This will become negative, this will become positive. That is a change. Did you get that derivation? Yes. Pawan Kumar Badger. Pawan Kumar Badger. Rajshekhar Torgal. Rajshekhar Torgal. No, you are not there in the class, both of you. Vivek. Yashasvi Kumbar.
Yes, sir.
I'm not asking about. Are you able to follow the derivation?
Yes, sir. Yes, sir.
So how do you find the sigma 1 and sigma 2 values? How do you get that sigma 1 and sigma 2? Which expressions will help me for finding sigma 1 and sigma 2? Okay. Right. Okay, we'll just look into some of the problems here. If you have any doubts, others, please unmute yourself. Don't keep muted. Just keeping the video on will not help you. You have to discuss every doubt, every single small doubt what you have. We are not in contact face to face. You have to come in and ask the doubts. If you are in physically present in the classroom, we can make out from your faces whether you understood or not. But here, you need to come and ask the doubt. You have to clear your doubts. It should not be a problem for you later. Okay, I'll just take one first problem here, right? So just remember the condition at least at this point, if not the complete derivation. So what you have is a rod is of 2 meter length and is at a temperature 10 degrees Celsius. Find the expansion of the rod when temperature is raised to 80 degrees Celsius. If this expansion is prevented, find the stresses induced in the rod. Take E is equal to 1.0 into 10 raised to 5 MPa and alpha is equal to 12 into 10 raised to minus 6 per degree Celsius. Okay, so this is what the problem is. We have a bar or a rod, okay, which is maintained at certain temperature. So initial temperature is 10 degrees Celsius. Okay, that is T1 is equal to 10 degrees Celsius, and later after some time the temperature is raised to 80 degrees Celsius. T2 is 80 degrees Celsius. Okay, so length of the bar is given to us as 2 meters. Okay, so what is the free expansion? That is the first thing what you have to find. Then after that, if that free expansion is prevented, what is the stresses that are developed? We'll see how that stresses will come in picture. Okay, so initially if I go for finding this free expansion over here, that is it is expanding to some length. Okay, so this is our delta or delta L, whatever you call. This free expansion has to be estimated. So it is given by what? This alpha into change in temperature, the coefficient of thermal expansion into change in temperature into the length. Okay, so this is the free expansion delta L. So what is my alpha value? 12 into 10 raised to minus 6 per degree Celsius into change in temperature is this T2 minus T1. So this is change in temperature T1. Okay, so alpha into T into total length 2 meters or 2000 mm. Okay, so this is what you get, delta L as 0.28 mm. This is a change in length. Okay, so this is straightforward, very simple. Okay, now what we want is next, if this expansion is prevented in this bar, okay, if that expansion of the bar is prevented, then what you find is the stresses will arise. So preventing expansion is that like this delta L is being pushed back. Okay, so I am applying a force and I am causing a this delta L to disappear. Okay, so actually there will be this bar will be having certain restraint or supports over here which will not allow it to expand freely if it is fixed at both these ends. Okay, like this. So, right, and if this change in temperature occurs, so it will not allow it to expand. Under such a situation, stresses will be developed here. So what is that? Stresses will equal to sigma. It is given by alpha T into E. Okay, alpha T into E. Same change in temperature is 80 to 10 to 80 degrees Celsius. So coefficient of thermal expansion 12 into 10 raised to minus 6. So alpha into T into E, Young's modulus is 1 into 10 raised to 5 here. Okay, so this is a Young's modulus. So what that gives us is 84 Newton per mm square. 84 Newton per mm square. These are the stresses that are developed. What is the nature of the stress? It is compression. When expansion is prevented, compressive stresses will get developed. When contraction is prevented, tensile stresses will get developed. You should keep that in mind. Okay. So when temperature is increased, material tries to expand. If you prevent that expansion, okay, so actually this was supposed to expand up to this point. Okay. So that has been prevented here. So the free expansion would have been something up to here like this. So this free expansion is prevented. So you are contracting this bar. It is just like contracting this bar. So because of that, compressive stresses will get developed. Please check. You will get this. Anybody, if you are have a calculator, if you are calculated, check that. One is free expansion, whether it will be 0.28 mm. The other is what are the stresses. Magnitude of stresses is intensity of stress is 84 Newton per mm square, and nature is compression. There will be compressive stresses. Do the calculation and just see, are you able to get those values? No?
The first answer is 16.8.
16.8. 12 into 10 raised to minus 6 into, this will be 70 into 2000. 16.8 mm.
Yes, sir.
So first one 16.8. What about the second one?
Second one is correct, sir.
Okay. Anybody else with any different answer? 16.8. It should not be so high. 16.8 mm. Anybody else who has done the calculation? 16.8.
Sir, it's 1.68, sir.
1.68, sir.
This is 1.68 mm. Okay. So this answer is 1.68 mm. So that's why. Okay. So this is fine. 84 Newton per mm. Okay. 1.68. Okay. What about this stress sigma? Is it 84 Newton per mm square or?
Yes, sir.
Okay, that is correct. Right. Okay. Fine. So then okay, let's do one more example on this. Okay, just take this problem here. You try this one. A steel bar is 20-meter long. A steel bar is 20-meter long at a temperature of 20 degrees Celsius. Find the free expansion of the bar if the temperature is raised to 65 degrees Celsius. Find the thermal stresses produced when free expansion of bar is completely prevented. 2. The rod is permitted to expand by 5.8 mm only. E is 200 GPa. Alpha is 12 into 10 raised to minus 6 per degree Celsius. Okay. So data is given to us here. You have this length L as 20 into 10 raised to 3 mm or 20 meters. What is given there? Okay. Temperature T1 is 20 degree Celsius and T2 is 65 degree Celsius. Okay, T1 and T2. Now E value and alpha value are there. So first is the free expansion. All of you try this one. We'll just try to find out what is the free expansion first. So this free expansion, okay, so that is delta L, we can call it. So delta L is equal to what? Coefficient of thermal expansion T into, yes,
10.8, sir. I got
10.8.
10.8.
Okay, okay, good. One answer we are getting is this is equal to 10.8 mm. Okay, this is the first case. Please try others. Second case, let me see what other answer will come. Free expansion. Okay, find the free expansion. In the question, what is asked here is find the free expansion of the bar. Okay, actually here in the question, I don't call this as a one. One is something else. So okay, just the free expansion. Okay, next, if you have found the free expansion, just know who said that answer 10.8 or okay, you can go for finding when free expansion of the rod is prevented, what are the stresses developed? Okay, you have to find what are the stresses developed in case one, what is sigma equal to. Try finding that one. I'll come to you. Others, please tell me what answers you have for this. I given the formula here. One answer, one, what I
10.8, sir.
10.8 mm. Okay, what will be the sigma then? Anybody remember this sigma expression? Just previous example or in derivation, what was there? Sigma was equal to when the expansion
Stress.
of the, yes, what is sigma? If you are telling the answer, see that you have unmuted yourself. That was very similar and simple expression for sigma. Sigma was equal to, just previous problem also we had the same case, delta L free expansion and sigma.
Alpha T E, sir.
Yes,
Alpha T E.
alpha T into what? Modulus of elasticity E. So this is sigma here. Okay. So what do you have? The stresses in this case?
So 10.8.
No, the stresses. It is also same. Here E is given 200
Yes,
GPa. Alpha is that same 12 into 10 raised to minus 6.
so same, sir. 10.8 Newton per mm square.
Same. Okay. Into this others. Please try that. 65 degrees minus initial temperatures 20 degrees into 200 into 10 raised to 3, 200 GPAs, 200 into 10 raised to 3 MPa, or that is 200 into 10 raised to 3 Newton per mm square itself.
So it's 108.
108 Newton per mm square, 108 Newton per mm square. Okay, so this is stress what will be developed when we completely prevent the expansion of that bar. Now, third case, when I come to third case, they are given something here. What they are told is if the bar is allowed to expand freely by 5.8 mm only. Okay, so what happens is up to 5.8 mm, you will not have any stresses developed in that bar. Okay, so beyond this 5.8 mm, the expansion is prevented here. Okay, so here this is 5.8 mm. Okay, so what you have is, so it can expand freely for a distance of 5.8 mm. Okay, so that is what you need to find out. Can anybody tell me how we can find that? This is 5.8 mm, this gap what you have here. So this is 5.8. Okay, this gap. Now after 5.8 mm, the free expansion will not occur. Okay, so only after 5.8 mm expansion, stresses will start developing there. So what may be the stresses in this case? Yes, any idea for that? How we can obtain what is the stress developed in this case? It is not completely restrained. Okay, it is restrained after 5.8 mm. Yes, the basic relation you can use, what? Stress upon strain is equal to modulus of elasticity, or stress can be expressed as this strain epsilon into modulus of elasticity. So E is given to us here. It is given to us. Can I find what is this strain equal to actually? Yes. In this case, what will happening is,
Change in length upon total length.
yes, change in length by total length. This should be the change in length. Okay, the free expansion. Okay, so that will be the change in length. But in this, some amount is restrained delta. Okay, so whatever is this delta in free expansion, if I deduct this, okay, I'll be able to find out what free expansion has been prevented here. Okay, so free expansion is something up to this point here. This is what? This is alpha into T into L. Okay, so this would have been the free expansion. Okay, but some amount of free expansion is prevented. That is, I'm bringing back this. Okay, by an amount alpha T into L minus 5.8. So this is this alpha T into L minus 5.8. So divided by original length we had taken in that expression into E. Okay, in one of the expression I mentioned about this. Here delta L was neglected in the denominator because it will be very small compared to L. So this is what we are going to use here. Okay, so this E, if I multiply, it will give me stress here. Okay, if it is a case of strain, I don't have to multiply this. So this is a strain. Later, this strain multiplied by stress should give me what is the, sorry, E Young's modulus should give me what is the stress. Okay, or stress will be equal to alpha T into L minus delta. The delta what I'm talking here is 5.8 upon L into E. Okay, so this will be stress. Alpha is this 12 into 10 raised to minus 6. T 65 minus 20, that is 45 degrees. L 20 into 10 raised to 3. Okay, and delta is what? Delta is this free expansion, whatever the free expansion is allowed. Okay, up to this there will not be any stresses developed. That's why I have deducted this. Beyond this, whatever the free expansion is prevented, this part, due to that the stresses will get developed in the bar. Okay, do you have, can you tell me what this will give you? Answer.
27, sir.
27. So one is 27 Newton per
Square.
mm square. Okay, any other calculation? 27 Newton per mm square. So that is the free expansion. Sorry, stress when the bar is free allowed to expand freely only up to 5.8 mm. Okay, originally the expansion, free expansion was 10.8 mm. In this expansion, only 5.8 mm is allowed now. Beyond this, due to 5 mm deformation, what is the stress that is being found here? This is nothing but 5 mm deformation. That change in length, 5 mm divided by original length into E. That is what is multiplied here. Is that okay? Others, if you have calculated? Yes. So this was the first answer, 10.8 mm free expansion. Okay. Then the second case. Okay. So what you have, if the bar is allowed to expand freely up to 5.8 mm, this is the expression for stress. And stress developed here would be, check this answer, check my answer. What you have got is 10.8. I'm getting it as 50 Newton per mm square. 12 into 10 is alpha, okay, into T 45 degrees into 20 into 10 raised to 3 length L minus 5.8 delta divided by the length 20 into 10 raised to 3 into 200 into 10 raised to 3. 200 into 10 raised to 3 GPa. There is some difference what I have calculated here and what you told. Any other person with any other value of sigma when free expansion is prevented? What I missed out here is what is the stress when complete expansion is prevented. That is, calculation is not showing up here.
So 50 is correct, sir.
What is that?
So 50 Newton per mm square. So
Is
sigma.
it 50? Change in temperature will be 45. Check this. 50 is okay. Answer.
Yes, sir.
Okay. Verify if any other answers you are having. Okay. So can you take this one? And at the same time, please post your USN in the chat box. Only the USN, complete USN. So this is one more problem of this thermal stresses. A steel tube. Okay. So try this one. Steel tube of 45 mm. You can take this question, put your attendance and exit, but take this question and try. And question will be up to this thermal stresses. Okay. For first I up to thermal stresses. What we are dealt till today. Problems on thermal stresses. You can leave for next class if you put your USN. Yes, sir.